From previous discussion, we come to know that derived quantities are obtained by repeated use of base quantities. We have seen many of the examples used in this video. So, the quantity which are used to form a new quantity are expressed in the powers. How? That means how many times base quantities are used to form derived quantity. When we write the powers of the base quantities to show the derived quantity, then we can say it as dimensions of the physical quantity. So we can say that, in another words, derived quantities are the combination of different 7 numbers of fundamental quantities. We can call these 7 fundamental quantities as the dimensions of the physical world, which are denoted by square brackets. Thus, the dimension can be defined as the dimensions of a physical quantity are the powers to which the base quantities are raised to represent the derived quantity. Let us write some dimensions of different derived quantities. So, dimensions for fundamental or base quantities are length L, mass m, time t, electric current A, temperature K, Kelvin, luminous intensity candela CD, amount of substance mole. So these are the 7 fundamental quantities, and these are the dimensions of all the 7 fundamental quantities. Now for derived quantity, how we can write dimensions? Let us say area is equal to length multiplied by breadth. Length, breadth or height, all are measurement of length. Therefore, we can write here L to the power 2, L square. That means 2 times value of L are used. So, it can also be written as a square inside the square bracket. Similarly, for volume also, it can be written under square brackets. So volume is the product of length, breadth and height. So 3 times length is used to derive volume expression. So it is L cube. Similarly, for density is the ratio of mass divided by volume. So mass single time used here, 1 time. So power of m is 1, and in volume length is used thrice, so power of L will be L3, and we brought volume expression in the numerator, so we have -3 power. So these are the dimension of density. Similarly, speed or velocity, we know that SI unit of speed or velocity is meter per second. Length is used 1 time and time is also used for 1 time, but those are in denominator, therefore t has power -1. Similarly, for acceleration, we know that for acceleration also length is used once and time is used twice, so it is -2. Then force is equal to mass into acceleration. So we already have dimension of acceleration and mass, so we will put directly and it becomes mLt to the power -2. We can solve for work, power, etc. Writing dimensions in this order is called dimensional formula. Under square brackets, if we write all the used physical quantities in this order is called dimensional formula. And if we write quantities and dimensional formula using equal sign, then these expressions are called dimensional equations. These are dimensional equations. The concept of dimension describes the basic important physical behavior, such as a physical quantity can be added or subtracted if they have same dimensions. For example, length of two different rods can be added. Difference between the mass of two different objects, or to write a equation, the quantities must have same dimensions. Here L1 is the length of the first rod, 5 meter. L2 is the length of the second rod, 4 meter. So total length of the rod, if they are joined together, if both the rod are joined together, what is the length of the rod? So it is L is equal to L1 plus L2. These two values can be added since they have same dimension L. Therefore, this is correct. More example of this is, let x be the displacement plus v is the velocity. Okay, here say dimension of displacement is L and dimension of velocity is L t to the power minus 1. Okay, both of them have different dimensions, so we cannot add these two quantities, displacement plus velocity. But if velocity is multiplied by t, that is time, okay, if velocity is multiplied by t time, then let us see what is the dimension. So here dimension for time t is t. We apply basic algebra for this to find out the power of t. Here t to the power minus 1 and in this t power is 1. So when bases are multiplied, then powers get added. So minus 1 plus 1 becomes 0. So dimension of Vt, velocity multiplied by time, is L. So we can easily add displacement plus velocity multiplied by t. So both of them have same dimension. Now it is possible to add x displacement plus product of velocity and time. The dimensional analysis also helps in deducing certain relationships and check the accuracy and homogeneity of the equation. Now, what is homogeneity? As I have told earlier, homogeneity means that the two different physical quantities cannot be added or subtracted unless and until they have same dimensions. The principle of homogeneity is useful in checking the correctness or equity of the equations. If the dimensions of each term of an equation is not same, then the equation is wrong. Also, the equation to be correct, it is the necessary condition that the dimension of all the physical quantities added in the equation or subtracted in the equation must have same dimensions. Let us consider the equation of motion. S is equal to ut plus half at square, where S is the displacement, u is the initial velocity, a acceleration, t time. So dimension for displacement is L, initial velocity is L t to the power minus 1. For acceleration, dimension is L t to the power minus 2. And for time is t. Here in equation half is a number, so a number has no dimension or dimensionless. The product of initial velocity and time gives us dimension L. The product of acceleration and square of time gives us dimension again L. So we can say that in the left side of the equation it is dimension L. Ut also give us dimension L. This one. Product of at square also give us dimension L, and half is a dimensionless quantity. So in this equation we have said that all the three terms have the same dimension. So we can say that S is equal to ut plus half at square is a dimensionally correct equation. If an equation fails this consistency test, that means dimensional correctness test, then the equation or relation is totally a wrong equation. But if equation is dimensionally correct, it doesn't prove that the equation is exact or 100% correct. Why? In the last equation S is equal to ut plus half at square, we have checked the correctness of dimensions. That means all the terms have same dimension L, and a constant half is there, which is a dimensionless quantity. So instead of half there is 3 by 2. If there is 3 by 2, then also the equation is dimensionally correct. Again, if S is equal to ut plus 3 by 2 at square, also a dimensionally correct equation. But half at and 3 by 2 at, which one is the correct value or which one will be the correct ratio, it doesn't prove by dimensional analysis. So we have to do experiments to solve this problem. Therefore we can say that if an equation fails dimensional consistency test, then the equation is exactly wrong. But a dimensionally correct equation is not necessarily a exact equation. Some of the quantities have no dimension, such as refractive index, purely numbers just like 4, 5, half, 3 by 2, 7 by 5. These have no dimensions. Speed by speed ratio, etc., has no dimensions.